Build It Green offers monthly webinars as part of our continuing education offerings and member benefits, as members receive free admission to our webinars as well as free access to our webinar library. This webinar and PowerPoint slides will be available for download in our members' webinar library by early next week, as well as, as I mentioned, the PowerPoint slides. And if you're not a member of Build It Green, we do hope that you will consider becoming part of Build It Green's member community and helping to support our work in California. Please visit our website to learn more. Okay, and so for today's agenda, I'm sorry, I have the wrong title up there. That's my mistake. It's from our last month's webinar. Today we're going to be breaking up today's presentation into two parts with a 10-minute Q&A after each section. And during the Q&A portion, you're welcome to type your questions into the chat box, and we will read them for Judy to answer. And to make it easier, if she's answering a question that pertains to a particular slide, she's included the slide numbers on her presentation, so please note the slide number, so that way if she needs to go back and refer to it, it'll be easier for everybody to follow along. And just wanted to remind folks today's webinar is worth 1.5 CEUs, but we can only give you credit if you stay on for the whole time. And you don't need to submit this course for recertification, as we will upload it into your record. Takes about a month, just to let you know. And at the very end, there'll be a very quick, brief survey that'll go out immediately after the webinar, and we appreciate if you could fill it out to let us know how we're doing with our webinar offerings. Okay, so this morning, we're very lucky to have with us Judy Roberson from the PG&E Energy Training Center. Judy is a residential building scientist and ventilation consultant at PG&E's Energy Training Center in Stockton. She earned an MS in architecture from UC Berkeley with a thesis on ASHRAE's Residential Ventilation Standard 62.2. While a research associate at Lawrence Berkeley National Laboratory, she supported Energy Star's energy efficiency programs, including new and existing homes. Judy learned building design and construction in Wisconsin, where she worked as an apprentice carpenter on multifamily housing projects, an architectural drafter for a residential design build firm, and apprentice architect on passive solar residential and small commercial projects. She has a BS and an MS degrees from Texas A&M University. Please say hello.
Thank you, Michelle. By the way, I'm not a PhD. I have 2 masters. It's really a pleasure. I appreciate Build It Green inviting me to do this presentation, and I appreciate the introduction as well. For the last, can everybody hear me okay? For the last 15 years or more, I have been working more or less full-time on this topic. Get my slideshow up there. And so I know my purpose here is to help everyone else who is trying to introduce themselves and deal with this new requirement in new California homes, and to share what I've learned over many years of trial and error and frustration, so that you don't have to go through what I went through. So we're going to start very, very basically, and we're going to get we're going to get to some pretty advanced technical topics before it's over. But you should know that that this is a very condensed version of a full-day class that I teach for PG&E at their training center. This disclaimer slide with all the fine print on it, you don't need to read it, but the important point is that neither PG&E nor I have any, we don't recommend or endorse any particular manufacturers or products. I personally don't have any vested interest in any of these systems. I think that's very important to know, that this information is objective. I'm not trying to sell you anything. This is my contact information. I expect that you'll have questions that I won't be able to answer in the time we have today, so you're welcome to email me at either of these email addresses. And in addition to that, we've just scheduled my full-day class for PG&E is called Ventilate Right, Build Tight. All PG&E classes are free to attend, and the website at the bottom of the page that you're seeing now is the URL for our all PG&E classes. So that website should be refreshed sometime on or after August 19th, 2011. So I encourage you to check that website and check out our full list of classes. And if you want to attend my full-day class this fall, it will be offered Friday, September 23rd in Stockton and Wednesday, November 9th in San Jose. The webinar consists of several modules. Basically, as Michelle said, we're going to break it up into 2 halves. I'm going to be hitting just mostly the high spots and the main points of my full-day presentation. And I'm going to ask you to, when we do have a Q&A session, to try to limit your questions to the material that I covered. And we'll do the best to get them answered. So all of us, sooner or later, that are involved with residential building in the United States and California in particular, have to deal with this topic. So we're all basically starting from scratch. And one of the first things that happens when you start trying to educate yourself about this topic is that you'll realize that it's very confusing, it's very complex, and it's very controversial. Now, I can't do anything about the controversy, but I will do my best to point out the controversial aspects when I reach them. But I do intend to help you navigate and minimize the confusion and the complexity by simplifying things as best I can. And we're going to start at the bottom, at the very basics. Everybody knows what HVAC stands for, right? Heating, ventilation, and air conditioning. This term comes from large commercial buildings where all 3 of these functions are met usually by mechanical systems. However, the V in HVAC has not really applied to homes or residential buildings until recently. So what does that V stand for when it comes to homes? Well, at its most basic definition of ventilation is simply movement of air. Now, if you think about it, and if we were in class together, I'd be doing this interactively, but I'm going to summarize the process for you. If you think about it, there's lots of types of air movement that we're already familiar with in our homes. And we're going to go through those in the next slide. But in general, you want to be aware that ventilation is either passive, meaning it's driven by the natural forces of wind and temperature, or it's active, which means it's driven by mechanical fans. And mechanical fans are the only driving force that we can control, so that's what we're going to use. This slide is an important summary slide. This is my best advice to help you and your clients and your colleagues avoid confusion when you're having conversations about different types of home ventilation. On the left column is a list of the most common types of air movement or ventilation in homes, starting with open windows and going all the way down to the last 2, which are in red font. Those are the 2 that we'll be focusing on today, but I want to mention and identify the purpose of all the other ones, so that to help you, as I said, understand the various types of ventilation and what their functions are. So the different functions are across left to right at the top. They range from cooling. It can be either cooling of people or cooling of spaces. That's right. Okay, that's fine. In the case of drying, attics and crawl spaces, we ventilate those passively or actively, primarily to dry or remove moisture from those unconditioned spaces, not living spaces, but unconditioned building cavities. Notice that for the purpose of moisture control, the only ventilation system that serves that function is intermittent exhaust fans. We're talking about bathroom and kitchen exhaust fans that are operated as needed by occupants to remove moisture and odors from rooms where they're generated before they can contaminate the rest of the house. Very, very important. Those have been required by code in most jurisdictions for decades, and the new code requirements are designed to improve their effectiveness. Indoor air circulation, we use ceiling fans. These are the paddle fans that people use in the summertime to cool people. When you use a ceiling fan in the summertime, it increases airflow across people's skin, which makes people have have a higher level of comfort at the same air temperature. You don't have to use your air conditioning so much. Likewise, ceiling fans improve indoor air circulation, particularly in the wintertime when you might need to de-stratify the air as the warm air rises to the ceiling and you want to bring it down to where the people are. That's a good function for ceiling fans. The other type of residential ventilation that's designed to optimize indoor air distribution or circulation, of course, is a central forced air heating and cooling system. These systems are the most common system in American homes, and we're going to be talking about whether and how to integrate that with ventilation later in the presentation. The final column on the right is indoor-outdoor air exchange. Now notice that the only two types that serve that purpose are open windows, which is what we have been using so far, and then finally at the bottom, this new mechanical system in homes, the new kid on the block, continuous ventilation for indoor-outdoor air exchange, which is the one that people are not familiar with. You notice I didn't put infiltration or uncontrolled infiltration on this list because it's not deliberate. It's not intentional. So basically, the takeaway from this slide and this portion of the presentation is that this new requirement for continuous ventilation for indoor-outdoor air exchange is necessary for all those times when people cannot or do not open their windows for whatever reason. The industry has acknowledged that we need mechanical ventilation to fulfill that purpose reliably. So now we're going to talk about indoor air pollutants, because mechanical ventilation, and we're talking about a residential context here, is not an efficiency measure. It's required by the California Energy Code, Title 24, but it doesn't save energy. In fact, it's a new additional electrical end use in all new homes. So why is it required by the Energy Code? Well, energy efficiency cannot and should not be achieved at the expense of health and safety. The purpose of mechanical ventilation and the code requirement is to protect occupants from indoor air pollutants. So if we're going to design and install and operate systems that do that, we need to understand the indoor pollutants that we're dealing with and how mechanical ventilation can best be used to control them. The subject of indoor air pollution is a huge one. For simplicity and to help everyone understand the practical aspects of this topic, I've boiled them down into three categories, and we're going to look at these one at a time briefly. The most dangerous potential indoor pollutants are ones that should never be in the home in the first place. I'm talking about basically combustion products, the most dangerous of which is carbon monoxide, which is lethal or potentially fatal. Ventilation systems can't control them and must not introduce them. The worst case scenario that the bottom line of what we're concerned about here is backdrafting of any combustion appliances. We're talking about gas furnaces and water heaters, primarily in California, that rely on indoor air for their combustion and venting process. In homes with these appliances, negative indoor pressure at very, very small amounts, as low as -3 pascals, can potentially reverse the flow of air out of these combustion gases out of the house and actually bring them into the house where people will breathe them and suffer as a result. So this is the primary concern about negative indoor pressure in homes with any kind of depressurization hazard, but especially this one. The second category of indoor air pollutants I call occupant source, and these are primarily moisture and odors, and they're generated pretty predictably in rooms with plumbing. We call them wet rooms, and that's why we put, and the code requires, exhaust fans in every bathroom now and over the kitchen range hood. Okay, I cannot overstate the importance of these fans and installing them, selecting, installing, and controlling them, and using them properly. Briefly, the bottom line here for bathroom or intermittent exhaust is at a minimum, we want to look for fans with the Energy Star label. Okay, they are required in every bathroom and kitchen now. The Energy Star label means that several things. First of all, they're high efficacy or efficiency, which means that they move relatively high CFM, or cubic feet per minute of air, for every unit of energy or watt. So high CFM per watt. They are quiet when they're operating, so people don't mind using them. This is particularly important in a kitchen situation when you're trying to carry on a conversation, and sometimes it's your family or the fan, and the fan usually loses. Also, if there are any lamps in the fans, like in the bathroom, the lamps are fluorescent and they can't be replaced by an incandescent lamp. Always want to duct all these fans directly to outdoors, not to some unconditioned space, and they have to have a backdraft damper, and they should be measured and verified after installation to ensure that they're moving at least the minimal amount of air. This is what they look like. For bath fans, they can either be installed in the ceiling, like the one on the right, or through the wall if the bathroom is on an outside wall, in which case there's no ducting required. Controls are very important. Now there's at least two kinds of controls for these bath fans, and this is an area where we don't have consensus. In my opinion, these fan delay timers like the one on the top are best because they give occupants a choice. Someone who's leaving a bathroom, they know how much moisture and odor in general they generated in that bathroom, and as they leave, they turn off the light and they can set the fan to run for anywhere from 5 to 60 minutes after they leave. I think that that choice is really nice, and these controls are very reliable. Another choice is a dehumidistat, like the one on the bottom. In this case, you would set the dehumidistat to about 50%, and then the idea is that the fan will automatically come on and operate as long as the relative humidity in that bathroom exceeds 50%, or whatever your set point is. You don't even have to be at home. More about dehumidistats later. But good controls, and some occupant control over bath fan operation is important. The third category of indoor air pollutants is basically VOCs, which stands for volatile organic compounds or chemicals. And these are a category of pollutants that has enormously grown over the last few decades. And even when we do our best through programs like Build It Green to select materials that with minimal VOCs, we're talking about building materials themselves, building finishes, and then whatever occupants bring into the home. Not all of these, even if you do the best job of keeping them out in the first place, there's going to be some residual VOCs in modern homes, and this is the category of pollutants that continuous mechanical ventilation is designed to control. We don't want occupants exposed to high levels of VOCs. So as a summary of controlling indoor air pollutants, we always want to exercise all of our source control options. For outdoor pollutants, that is primarily installing sealed combustion appliances that cannot be backdrafted by negative indoor pressure. For occupant source pollutants, we want to use intermittent exhaust fans effectively. And for VOCs, we want to eliminate as much as possible the VOCs that we install permanently in our buildings. And finally, after we've done all those things, then a small continuous mechanical ventilation system has a chance of controlling the remaining VOCs that cannot be removed at their source. The next module is continuous ventilation for indoor-outdoor air exchange. This is just an introduction. It's going to be very brief. One of the first things you'll find when you start talking to distributors or suppliers or contractors is all these systems have lovely names that don't describe what they do. So you can save yourself and your clients a lot of trouble if you understand that no matter what a system is called, it's one of these three functional types. It either uses an exhaust fan, a small exhaust fan to remove indoor air, which creates a negative pressure in the house, which basically sucks outdoor air in through the paths of least resistance over which you have no control. Okay, it's basically indirectly inducing infiltration for the introduction of outdoor air. The second type is the opposite of the first. It's called supply. You use a similarly sized fan, but you reverse its orientation with respect to the house. And in that case, the fan is basically pumping outdoor air directly into the house, which creates a positive indoor pressure and pushes the indoor air out through the same paths of least resistance. The third type is a combination of the first two. It's called balanced because it uses both an exhaust fan and a supply fan to move the same amount of air at the same time but in opposite directions. And if it's installed that way, a balanced system does not affect the indoor pressure. All right, so why is this code requirement happening now? Well, it's basically a trifecta of three circumstances that are coming together or have come together over the last few years or decades. New homes are tighter than they used to be. There are more sources of indoor air pollution, including attached garages and the VOCs, whatever the people bring into the house, and also more reasons to keep windows closed. Nobody is saying that you cannot and should not use your windows as much as you want to. Absolutely not. We're just acknowledging as an industry that there are lots of reasons that people don't use their windows as much as they might even like to. And I'm not going to read through all these, but you can see that there's lots of them. So nobody's dissing windows. Occupants actually will have an on-off switch. They can choose not to use their ventilation system if they want to rely on their windows, as long as they know what they're doing. So here's a conceptual version of the paradigm shift that we're currently undergoing as a nation and in the state of California as well. We're shifting from leaky homes that were ventilated by uncontrolled infiltration to tight homes that are ventilated by controlled mechanical ventilation. Now, there's all kinds of advantages to the mechanical ventilation paradigm, but in reality, we're not there yet. Where are we in this process? We're somewhere in the middle of the road, which is not a good place to be. That's why my class is called Ventilate Right, Build Tight, because in California we're being required to learn how to ventilate homes. And once we do that, and I'm not diminishing the steepness of the learning curve here, but once we can confidently and competently ventilate our homes, there's nothing to keep us from tightening them as much as they need to be for all kinds of reasons, not just including energy efficiency, but comfort and passive survivability, lots of benefits. So we need to get out of the middle of the road, learn to ventilate right, and build tight. When I talk about sizing ventilation systems and ventilation codes, we're going to be talking about minimum requirements. What I think everyone needs to know is that there is no one single ventilation rate that is appropriate for even one house over time with its occupants and activities, especially not for all homes all the time. However, we do have guidelines for minimum ventilation rates, and those guidelines tell us basically at least 0.35 air changes per hour, which is about the equivalent of a full house air change every 3 hours, up to a minimum of half an air change per hour, or a full air change every 2 hours. Okay? Keep that in mind. Ventilation, when we talk about controlling building airflow, we need to understand what the three driving forces are. I've mentioned them already. The first two are natural and beyond our control. The third are the mechanical fans that we will rely on for controlled ventilation. The industry, the residential building industry, including the ASHRAE body that created the standard. By the way, ASHRAE stands for American Society of Heating, Refrigerating, and Air Conditioning Engineers. We realize that the natural forces are unreliable and inconsistent. In fact, if you're relying on holes in your house and natural driving forces for your outdoor air supply, you're going to receive a lot more outdoor air than you want when you least want it, which is in the wintertime when you're trying to keep warm. And it's also important to know that ventilation and building air tightness go together. This is the bullet on the bottom of this slide. It doesn't make any sense to ventilate a house that isn't tight, and it doesn't make sense to not ventilate a house that is tight. So these ventilation and air tightness are two sides of the same coin. Moving on to minimum California code requirements, I'm going to just tell you what the minimum measures are. This, starting with Title 24, 2008, which was effective January 1st, 2010, it is a mandatory feature, not optional. You can't trade this off. For low-rise residential buildings, you have to meet ASHRAE Standard 62.2. You can no longer rely on windows to provide adequate outdoor air. So what does Standard 62.2 say? It says, this is a quote, you have to use either a mechanical exhaust, supply, or combination thereof. That's the exhaust, supply, and balance system that I already described. Any of those will work. They don't tell you which one you have to use. The equation is from 62.2, and my translation of it, which is intended to simplify it, your understanding of it, is that the minimum mechanical CFM required is 1 cubic feet per minute per 100 square feet of conditioned floor area, plus 7.5 CFM per occupant. So, for example, if you have a 3,000 square foot house, the first component would amount to 30 CFM, and if that 3,000 square foot house has 3 bedrooms, we would assume 3 plus 1 or 4 occupants. That's the occupancy assumption for new homes or homes that are unoccupied. That would also be 30 CFM, and they would add up to 60 CFM for that particular house. Now, if you don't want to use this equation, you can use the table from ASHRAE 62.2, which is on this slide. And notice in the table, if you look at 3,000 square foot house with 3 bedrooms, there's the 60 CFM. Now, it's important to know that these are absolutely minimum requirements, not necessarily targets. Fans can, and in my opinion, should be larger. These CFMs in this table, the standard does not, these need to be confirmed through measurement or prescriptive duct sizing. You cannot rely on a fan rating on a box to assume that it actually delivers these CFM. In addition, these minimum CFMs are based on continuous operation. If for any reason you decide you want to operate your ventilation fan intermittently, less than 100% of the time, which is 24/7, 365, then the fans have to be larger. At a minimum, for example, if you want to operate your fan 30 minutes out of every hour, let's say 20 minutes out of every hour, which will come up later, then instead of our 60 CFM minimum, when the fan does operate, it would have to admit 180 CFM of air, which is 60 times 3. For local exhaust fans, at least 50 CFM exhaust fans that's delivered intermittently in every bathroom, and at least 100 CFM intermittently in the kitchen, and ideally that's over the range hood, even if there's a window. These have to be ducted to outside, not some intermediate space. And in addition to the Title 24, 2008, there is a new 2010 California Green Building Code, which has additional requirements affecting bath fans. It required, this was effective January 1st, 2011 of this year. So it requires that all these fans be Energy Star compliant or labeled, which is good. Also requires that they are controlled by a readily accessible dehumidistat with some adjustability to it. And this applies only if the bathroom contains a tub or shower. It doesn't apply to toilet compartments. Okay. This is an important slide, prescriptive depressurization limits. This has to do with needing to minimize the negative indoor pressure in homes with natural draft combustion appliances, basically gas furnaces or water heaters. And it says that the sum of the 2 largest exhaust fans in the house cannot exceed 15 CFM per 100 square feet of floor area. Now, usually, the 2 largest exhaust fans are your clothes dryer, which is tends to be a minimum of 150 CFM, and your kitchen range hood, which by code is at least 100 CFM and can be much larger. So, for example, in a 2,000 square foot house that has an atmospherically vented water heater, your exhaust CFM cannot exceed according to this simple equation, 300 CFM. So 100 CFM range hood, 150 CFM clothes dryer, 250, you can see that you would easily be bumping up against this prescriptive depressurization limits. The best advice is don't install natural draft combustion appliances in new homes. Only install sealed combustion appliances. There's also a table of prescriptive duct sizing because even exhaust fans, unless they're through the wall, have to be ducted to the outside. And this table tells you if you want to the extent that the Title 24 requirements are going to be enforced, your ducting is either supposed to comply or be described by this table, in which case you don't have to measure the airflow or verify the airflow. If it can't be described by this table, then you are supposed to measure and verify the airflow after installation. So basically what this tells you is, first of all, you're either using flex duct or smooth duct. If you're using flex duct, you have fewer options. You have less length to play with. X means it's not allowed at all. So you can't use 3-inch flex duct for any of these fans, for example. You'd have to go up to a larger diameter flex duct, and NL means no limit, meaning that if you're using that type of duct and that length of duct, then or that diameter duct, then there's no limit to the length that you can install. One more slide on California requirements. Every continuous ventilation system has to have an on-off switch, and it has to be labeled. Consider the occupants. I mean, these systems are new to everybody, especially the people that are buying and living in these houses. So we have to be, as conscientious professionals, and this is also a code requirement, if we need to label the switch as controlling the whole house ventilation system. And so if people maybe hopefully they're not aware of their ventilation system. So they see the switch and they might want to turn it off. What is this? How many times do you do that, right? You flip a switch to see what changes. Nothing changes, so you leave it off. Well, that's why this switch has to be labeled. So if people turn their system off, they know what they're doing. Okay, and it also has to be accessible. You can't put this switch in the attic or the crawl space where people can't find it. Sound ratings for fans that are mounted in living space, if they're continuous, they have to be less than 1 SON, which is very quiet. A SON is a linear unit of sound, unlike decibels. If you come to my full-day class, I will have my fan club, which is a variety of ventilation fans that we can use for these purposes, and we can demonstrate what a SON or a 1.5 SON sounds like. It's basically not objectionable. To minimize indoor air pollution from an attached garage, the code says you have to weather strip doors to the attached garage and otherwise isolate the garage as much as possible. Dryers must be vented to the outside. If you're using a supply fan, it has to have at least a MERV 6 filter on it, which is a minimum efficiency filter for residential supply systems. And if homes are attached, like duplexes or townhomes, you're supposed to minimize air transfer between adjacent homes, even though it doesn't give you a performance basis for that or tell you how to do it. When it comes to actually verifying compliance on your Title 24 paperwork, there is a new form, CF6R MEC 05, and the information that you're going to need to provide on that. For local exhaust, you have to tell them what your minimum required airflow rates are, not necessarily what you installed, just what the minimum is. For the whole building ventilation system, you have to tell them what the minimum airflow is based on standard 62.2. You have to tell them what type it is. That would be exhaust, supply, or balanced. You need to provide the installed fan make, that's manufacturer, model, and their rated performance in CFM at static pressure. And if a central air handler fan is used for supply ventilation, you're supposed to verify that that fan uses less than or equal to 0.58 watts per CFM of total system airflow. And as I mentioned before, when we were looking at the table of prescriptive duct sizing, your your ventilation ductwork either has to conform to the specs in that table or it's supposed to be measured. All right, how are we doing on time? Doing great, pretty good. So that's a quick flyby of the first half of the webinar, so I'm ready to take questions now on what I've already covered.
Great. Well, we already have a question that's come in from Brent Kuhn. He says, Calgreen says it requires dehumidistats for intermittent fans, but can this be replaced by a timer?
Well, I haven't, I think the answer is basically no. The way around that, if you want to use a timer instead of a dehumidistat, is to, I should say that if you run the fan continuously, that requirement doesn't apply. So that's the only way around that requirement for a dehumidistat that I know of. Another option might be to, and this is more trouble, I think, but to provide a dehumidistat, but also provide a timer. And then you can use the timer in addition to the dehumidistat.
Okay. I had a question just about, you said the best is fan delay and the humidistat was good. Why is that? I would think that, like, I know for myself, like, how do I know how much time it's going to take to properly, vent the shower that I just took, right?
Well, you figure that out by trial and error. I used to recommend dehumidistats. That used to be my top recommendation. But then I got feedback from people in my classes and feedback from the field and things that I read and heard that the dehumidistats actually aren't very reliable. When they work, they're fine, but they tend to stop working after about 6 months. And so I think that's a significant, significant issue that we need to deal with.
Now they're code.
And now they're required by the California Green Building Code.
Wow.
And by the way, there is a third option for controlling these systems. For example, Panasonic, which is one of the major manufacturers of Energy Star label fans, they don't use dehumidistats. They don't make any fans with integral dehumidistats. They use occupancy sensors. Okay, so that's a third option. So if you want to use a Panasonic fan and comply with the California Green Building Code, you're either going to need to buy a 2-speed fan that can operate continuously on low speed, which would then negate the requirement for a dehumidistat. And by the way, that type of fan that I'm talking about, a 2-speed fan, can be used to meet both of these new requirements. So you would operate it on low speed continually to meet the continuous ventilation requirement, and then you would have a control that bumps it up to high speed when you need the intermittent ventilation to purge your bathroom of the moisture and odors.
Okay, cool. All right, we've got a bunch of questions, so we should get through them. Ken Brooks says that he hears there's an Apple application for stone measurements.
That's new to me. I don't know about that. I'd like to hear about it. Please send me an email, Ken.
And we have a question from Gretchen Ross. Can a forced air furnace also function as indoor-outdoor air exchange when it's not being used for heating?
The answer is yes, and we'll get to that in the second half.
And Fergus O'Sullivan asks, where and when is your full-day class that you mentioned?
It's back on one of the first slides. I believe it's September 23rd in Stockton. Thank you. September 23rd in Stockton and November 9th in San Jose. And again, you can go to, if you're not familiar, if you haven't taken any PG&E classes before, that's something to look forward to. Bookmark this URL in your browser, www.pge.com/energyclasses. We have 2 semesters every year. We're at the end of our spring-summer semester now. The fall classes will populate the website on or just after August 19th, which is a little less than 2 months from now. And not only my class, but hundreds of other, certainly dozens of other PG&E classes will be available there as well. They're free to attend, but we ask that you pre-register so that we know how many people to expect.
Great. Ken also asks, any feedback on accuracy of it? And our stone measuring device is expensive. Maybe he was referring to the Apple application. But but I guess the question would be, are stone measuring devices expensive?
You know, I don't know that. But I will say that the zone measurements that manufacturers put on their products are required to be measured independently by the Home Ventilating Institute. So those are laboratory measurements. Okay, now if there is a device or an application available to measure zones, that's fine, that's great. But when it comes to code compliance, they're looking for HVI rated zone measurements.
So you actually don't need to invest in having something measured.
No, and by the way, I think this is a good time to say that you can only rate the zones of a fan that's installed in a ceiling. If you have a fan that's installed remotely, whether it's an exhaust fan, an HRV, or a supply fan that's not installed in the ceiling, not only is it are they not rated for zones, but it's not possible to rate them for zones because there are so many variables in that installation process. So zone ratings do not apply to remotely located fans.
Okay. All right, moving on. Eve asks, will we be going into more detail on combustible sealed exhaust systems?
No, not in this webinar.
Okay. We have a live question here from Chris Knudsen.
Okay, how often do builders test for vent system flow? What are they finding? Have third-party verification studies been done? Very good question. I don't know the answer. As far as I know, no builders are, I don't know of any builders who are actually independently verifying their own system airflows. So I don't know what they're finding. The only study that I know that dealt with this was a study recently published. It was published about a year ago. It was conducted in 2004 and 5 by Bud Offerman. The study was commissioned by the California Air Resources Board, and he and his team did extensive measurements of many ventilation and indoor air quality parameters in two populations of California new homes, one in Southern California and one in Northern California. And they got lots of very interesting data, even though it was a limited population. I think it was just over 100 homes. That's the only data I know of that's independently measured and available. And if you want to send me an email, I can send you links to that report and presentations based on it.
And we're going to go forward with a few more questions. Mark Moritz asks, is mechanical ventilation absolutely required for all new homes, in addition to the required bathroom and kitchen fans?
Yes.
Great. Craig asks, there is an exception to 62.2-2007 for allowing windows to be used for ventilation. It's 8.3.1 and is allowed if the CBO and the local jurisdiction recognizes windows open as a ventilation source. The City of Santa Rosa and the County of Sonoma CBOs both recognize this exception based on our climate zone.
Okay, but the State of California does not. So that's a very astute question. And in fact, if you're really familiar with 62.2, it makes it a climate exception for these requirements. And in fact, most of California would be exempted based on the climate exception, except the Energy Commission chose not to take that climate exception. They overrode it, and they're requiring it.
Right. Okay. Mark also asks, would an attached in-law unit require its own separate switch to mechanical ventilation?
If it has a separate ventilation system, it has to have a separate switch.
Okay.
If it shares a ventilation system with another part of the house, it doesn't.
Okay, and then Craig asked a follow-up question. He said, please ask Judy to comment on this exception versus requiring builders to install energy-consuming ventilation systems. And I'm not sure what that was referring to.
Well, I will say that this first round of this 2008 Title 24 Energy Code requirement for mechanical ventilation is a first step. It does not yet address the relative energy efficiency or even effectiveness of the systems that it is possible to install. That's what I'm all about, and I'm hoping that, well, later in the presentation I will talk about the relative efficiency and effectiveness of various types of systems. So that's why this webinar is called Code Minimum Requirements and Best Practices. So far, I've just talked about the minimum requirements. There's lots of ways that you can improve on the minimum code requirements.
Okay. One final question is, how do you measure and verify the airflow after installation of an exhaust fan?
Well, there's several ways you can do it. The most accurate way is with a low-volume flow hood that's designed. You put it over either the supply or the exhaust grill, and you measure accurately the amount of air going through that. That's an expensive piece of equipment, though. Other ways to do it are to use an anemometer, which measures airflow in feet per minute or feet per second, and you multiply that by the net-free area of the grill. The cheaper equipment, the more difficult process. And there's even something called a calibrated garbage bag method, which LBL has a report on how to do that. So the Energy Commission, as far as I know, doesn't tell you how to do that, but those are the three methods I'm aware of.
And you were recommending to do that, and the reason I asked, is that something that would be done in, say, a home performance test in, test out?
I think it should be part of any home performance contractor's toolkit.
Okay. All right. Oh, very quick one. Is mechanical ventilation required for remodels?
Only at this point if the remodel involves an addition of 1,000 square feet or more.
Okay. All right. So we should move on with the second half, and then we'll take time at the end. So again, you can type your questions as we go, if that's easier for folks.
Great. Okay, so let's move on. So from now on, I'm going to be talking about best practices. This is basically my professional opinion about how to help you figure out how to select, design, install, and operate a system. So when any of us go out there, we have a home that we need to design and install a ventilation system for. We haven't done this before, or maybe we have. I think it's really important to have a shopping list. So this is my recommended shopping list for you. Now, no one system is going to have all of these qualities. Trade-offs are involved. By the way, there's no silver bullet, especially when it comes to this continuous ventilation systems. So here we go. We want to do no harm. We want to be careful about installing exhaust or depressurizing homes with any depressurization hazards. At a minimum, we want a high-quality fan, Energy Star labeled at a minimum. We want to size that fan to actually deliver whatever minimum ventilation rate we decide we want, as long as it meets or exceeds the code requirement. If we want to deliver a higher ventilation rate, we size the fan to deliver that, and that's the only way to ensure that minimum ventilation rate. Continuous operation is very important. There's many benefits to operating a small fan continuously instead of a larger fan intermittently. I'll go into that in more detail in a minute. Anytime we can filter the outdoor air that we're bringing into our home and temper it at least slightly to take the edge off of any hot or cold outdoor air, that is a huge advantage. And it's not enough to just dump a certain amount of outdoor air into a home. We really need to pay attention also, if we're concerned about best practices, we need to do our best to optimize the indoor distribution of that fresh air. And like it or not, that means that good ducting is involved. Not ducting for its own sake, but ducting for good air distribution. And then finally, a fan, especially if it has a filter in it, needs to be accessible for maintenance. So there's our shopping list. Before we go on, it's very important. You always want to consider the occupants. If you don't, you'll make mistakes and learn the hard way. But keep in mind that your occupants, your clients, the people who will be living in these homes need information about why they need a ventilation system, what kind of ventilation system they have, how and why to operate it, and of course, how and why to maintain it. And lessons learned from the field, we know from experience, painful experience, that occupants will disable a system and be very unhappy with a contractor who installs a system that is noisy, drafty, and or expensive to operate. So don't do that. Okay, so those standard 62.2 ventilation rates that we saw in the table in the equation, most people don't know this, but they do not correspond to the minimum 0.35 air changes per hour. They actually correspond more or less to about 60% of that, or a fifth of an air change per hour. Okay, and the standard, for whatever reason, assumes that infiltration, uncontrolled infiltration, makes up the remainder. Okay, so that's important to know. So 0.2 or the standard 62.2 CFM is your minimum, but if you want to deliver 0.35 or anything higher, there's a very easy way to size a fan to do that. And that's what I'm going to show you, I think in, well, okay, not the next slide, this slide. This is really powerful information. It's going to sound like common sense, but the problem is it's not common enough. As I hope I've already made clear, the only ventilation that we can count on is the ventilation that we control, which is the ventilation that we provide, that we deliver by mechanical means. So here's some good advice. If you want to ensure any minimum ventilation rate, as long as it meets or exceeds the code, size your ventilation fan to deliver that rate and operate the fan continuously, and you have done your job. In that case, any actual infiltration, which is driven by uncontrolled natural forces, or any window opening behavior on the part of the occupants, is supplemental to that, and that's fine. So here's how you do it. In this example, I'm using a minimum ventilation rate of 0.35 air changes per hour, which I got from somebody else. I'm not saying that's the right number. I'm saying that that's the number that most people are familiar with. So it's a very simple process, very simple math. The first thing you do is you calculate the volume of the house, which is one air change. So the volume is the floor area divided by the average ceiling height. In this example, it's a 2,000 square foot house with a 9-foot average ceilings, so it has 18,000 cubic feet per air change. You multiply that by 0.35 air changes per hour, divide by 60 minutes per hour, and it gives you a fan size of a little over 100 cubic feet per minute. And I would guesstimate that for typical moderate-sized houses in California, these fans, if you want to size them to deliver 0.35, they're going to be on the order of 100 CFM, as opposed to the 60 CFM for a similar sized house, which is what we saw in the ASHRAE table. So that's really, I think that's really powerful, simple, enabling information, and I hope you make the most of it. Really important to understand the benefits of continuous ventilation. Continuous means all the time. You really don't want to turn these things off. If you remember, the pollutants of concern for these systems are VOCs, right? Now, we don't necessarily smell, we certainly can't see VOCs, but we know from Bud Offerman's research study, which I mentioned earlier, that when and it just makes sense as well, whenever your ventilation fan is turned off, the indoor VOC, or volatile organic chemical, levels start to rise. Okay? And the longer the fan is off, the higher the VOC levels get. So even if people say, oh, you only need to ventilate when you're at home, you can turn it off when you're at work or school. No, that would be true if the pollutants of concern were moisture and odors, but that's not true. We're concerned about controlling VOC levels. So I would say, unless the home is foreclosed and vacated and unoccupied for months at a time, you don't want to turn the ventilation system off, even if you leave for a week or a month's vacation. That's my opinion. That is the most effective thing you can do to control occupant exposure to VOCs. There are other benefits of continuous ventilation, most notably the fact that if it's a small fan, a small, quiet fan operating continuously all the time, then it's going to be operating in the background. It's going to be not noticeable to occupants. As soon as you start increasing the size of the fan, which is what you have to do with intermittent operation, then it becomes, people start to notice the on and off noise, the on and off drafts, and then you have occupants who aren't happy with their ventilation system. Outdoor air filtration can only be accomplished by supply fans. You can't filter the air that's coming into your house if you're using an exhaust ventilation system. So that means if you want to filter the outdoor air, you have to either use supply ventilation or balanced ventilation, which includes a supply fan. The facts about filters of any type in any system is that if you include an air filter, you have to account for the additional system static pressure or the resistance that the fan has to work against to push that air through the filter. And the filters must be accessible for changing, and occupants need to understand why and how to change their filters. The filter rating system that we're using is MERV, which stands for Minimum Efficiency Reporting Value. There are basically 3 categories. For homes, we want to stay in the range of MERV 6 to 13. HEPA high-efficiency filters have their place, basically in institutional environments or specialized residential appliances like vacuums. But we don't want to put HEPA filters on our ventilation systems in general because it's just too restrictive on the airflow. Air distribution basics, okay? Unlike forced air conditioning systems where ideally we supply and exhaust air from the same rooms, with ventilation we exhaust and supply to different rooms. You always want to exhaust indoor air from the rooms with plumbing, and you supply outdoor air to the rooms where people spend the most time, which is primarily bedrooms, especially when people spend, if we're lucky, we spend 8 hours a day in our bedrooms sleeping. And then also living rooms, family rooms, offices, things, rooms like that. A very general overview of the quality of indoor air distribution. Again, it's basically based on ducting. I'm not talking about just any ducting. We're talking about well-designed, well-installed duct systems. And the bottom line here, I haven't gone over these ventilation systems yet in any detail, the ones that are listed on the right, but the poorest indoor air distribution is provided by a system with basically no ductwork, which is a single port exhaust system. The best indoor air distribution is provided by a balanced heat recovery system if both supply and exhaust streams are ducted. And in between we have supply systems where the supply airstream is ducted directly to where we need it, which is good. And then there's something called multi-port exhaust, which instead of exhausting from one point in the house, it exhausts from more than one point in the house, and that improves indoor distribution a little bit. Ventilation system costs. They fall into 2 big categories. There's the first cost that the builder sees, the cost of the system and installing it, and a little bit of maintenance cost after it's installed for the owners, like filter replacements, that sort of thing. And then there are operating costs, and the operating costs fall into 2 categories. There's the energy used by the ventilation fan, and we can predict these fairly well, and I'll show you how to do that in an upcoming slide. Then there's also the energy required by the heating and cooling system of the house to temper the outdoor air that is introduced by the ventilation fan. And this operating cost varies widely depending on variables like climate, your heating and cooling system efficiency, the type of fuel you're using, and the cost. So we did some rather extensive engineering modeling when I was working at LBL to estimate these costs. But it is complicated to estimate the tempering cost as opposed to the fan cost, which is relatively easy. And here I'm going to show you how to do that. So if you want to estimate what it costs to operate any particular ventilation fan, first you need to know your average cost per kilowatt hour, whatever that is for your home or your area, and your ventilation fan CFM. Then you use this equation and you fill in the blanks as best you can, and the output is your dollars per year. So for example, for a continuous bath exhaust fan at a 11 cents a kilowatt hour, which is the lowest residential rate in California, that's what I pay. So it's 11.4 cents per kilowatt hour divided by 1,000 watts per kilowatt, which doesn't change. If it operates continuously, then that's 8,760 hours per year. You divide it by the fan efficiency, which in this case I'm using 4 CFM per watt. That will vary depending on your system. But I have a slide at the end of this presentation which will give you a ballpark estimate for all these systems. And then you multiply finally by your fan CFM, and in this case it comes out to $26 a year, which is peanuts for this particular system. Actually, this is the lowest. Actually, it's not the lowest. It can be lower than this if you have a more efficient fan, like a Panasonic Whisper Green fan. They have 8 CFM per watt efficacy, which would be half of this. But this is pretty low. All right, so that's the end of my my shopping list and my description of best practices. Now we're going to talk a little more detail about your options for these and the pros and cons for exhaust, balance, and supply ventilation systems. Before we do that, I need to make this point that I want to reinforce the point that good ventilation and tight homes are two sides of the same coin. We can't avoid pressure in homes. In fact, the tighter the homes get, the more they're going to be pressurized and depressurized by any driving force, natural or mechanical. We know that the tighter the house, the easier it is to condition indoor air. That's good. The easier it is to control indoor-outdoor airflow with a mechanical fan. That's also good. However, the tighter the house, the more easily and the more often it will be pressurized or depressurized by any driving force. That's a reality that we need to accept. And we need to, I say this because people get nervous when we talk about pressure in homes because the only pressure they're familiar with is negative pressure. And that is a concern. It's a potential backdrafting hazard, and even without combustion appliances, there are reasons to be concerned about negative indoor pressure. However, it's important to know that because we can control fans and we can use supply fans, not all residential indoor pressure has to be negative. In fact, positive indoor pressure in California's climate in particular has many advantages. It basically, by directly delivering outdoor air to the space for fresh air, you're also pressurizing the house, which helps prevent outdoor air pollutants from being drawn into the house through the path of least resistance. And it also, this is not its intended purpose, but it effectively provides some makeup air for any combustion appliances or exhaust fans that tend to depressurize the house. So this is a best practice slide. This is not anywhere in the code. It's not even addressed. But based on my research and the work I've done, basically for my master's thesis, these are guidelines for how tight homes should be if you're going to install either an exhaust or supply system. Ideally, we want tightness targets that should be less than or equal to 3 air changes per hour at 50 pascals as measured with a blower door. For balance systems, it's even more important that homes are very, very tight. And based on what other countries recommend or require, and also the passive house requirements, we're looking for, with balance systems, homes that are less than or equal to 1 air change per hour at 50 pascals. Very few of our homes in California are that tight, even new ones. But these are targets for us to have on our horizon and for us to be shooting for. And the equation at the bottom is a very simple calculation of how you take a blower door measurement and calculate the ACH 50. It's very easy to convert CFM 50 to ACH 50. For example, if your blower door reading is 1,000 CFM 50, you multiply by 60 minutes per hour and divide by the house volume, and you have your ACH 50, which in this case is 2.8. Okay, so let's talk first about exhaust ventilation. This is the most affordable and easiest. Now, I should back up for a minute and say exhaust ventilation. This is a point of potential confusion because we definitely always want exhaust fans in our bathrooms and our kitchen for intermittent moisture control, right? But also exhaust ventilation, exhaust fans can also be used to meet the continuous outdoor air supply requirement. And so that's what we're talking about here. In places in this country where it's already required for homes to have continuous mechanical ventilation, exhaust fans are the most common type installed because they're familiar, they're affordable, they're very efficient to operate in terms of fan cost. However, we can't control where the air is coming from. It's just as likely to come from our attic, garage, or crawl space as it is from some nice clean spot on the outside of the house. We can't filter the air, and it does contribute to negative indoor pressure, which increases the likelihood of bringing outdoor pollutants indoors. In terms of indoor air distribution, any exhaust fan, the distribution aspect is limited by any closed doors. You close the door to a bedroom, you prevent the exhaust fan from being able to ventilate that bedroom at night. Exhaust ventilation basics in general, exhaust ventilation systems in general should not be used in tight homes with depressurization hazards. As I mentioned before, they can be either single port or multi-port exhaust. And these do have a role. As I said, they're the most common system used in the U.S. currently where it's required. And they can be very effective, especially in small, tight homes with open floor plans and little resistance to indoor airflow, in other words, interior doors. Here's a diagram of a multi-port exhaust fan. Same concept, only you're picking up from several points instead of one. Slightly improves the indoor air distribution. In summary, exhaust ventilation is the easiest, cheapest, and most energy efficient way to meet the Title 24 requirement for continuous ventilation in new homes. That's good to know. However, it has its downsides, which you need to be aware of. Now we're going to talk about balanced ventilation at a basic level. These systems are typically, they don't always, but they typically include, they're engineered systems that include a heat recovery or an energy recovery core. Because they're engineered systems and they have two fans and then they involve ductwork, they are the most expensive to buy, install, and operate, even though, keep in mind, they are designed specifically for this purpose, and then when installed properly, they do a great job of it. The operating costs are higher because you're paying to operate two fans at the same time. Because it includes a supply fan, you're able to filter the outdoor air, which is a tremendous advantage. Again, you exhaust air from different rooms that you supply air to. The real advantage of these systems is not a balanced indoor pressure, which is not really possible. Remember, I think I talk about this in the next slide, I think. The real advantage of these systems is that because you have two air streams, you can cross these air streams in a recovery core and transfer energy or heat from the outgoing airstream to temper the incoming airstream, which definitely improves comfort and can lower your operating cost, your tempering cost, depending on your delta T's. These are designed and they are used extensively in very, very cold climates where they have high delta T's in the winter, and delta T is the difference in temperature between indoors and out. So in really, really cold climates, these things really do pay for themselves. The savings in tempering costs makes up for the cost of operating two fans. However, they are susceptible, very susceptible to installation defects. So you want to always commission these things to make sure after they're installed that they're actually operating properly. There is a misconception out there that balanced ventilation is best because it maintains a neutral indoor pressure. The reality is that that's not really possible. Remember that balanced ventilation systems, if they're truly balanced, they do not affect indoor pressure. But that's very different from maintaining a neutral indoor pressure, which is virtually impossible. Because other driving forces, including other fans in the house, are pressurizing or depressurizing the house all the time. And remember, we have a third option. It's not just negative pressure or neutral indoor pressure. We now have positive indoor pressure, which is, in my opinion, much better than neutral because it has positive active advantages. So again, the real advantage to balanced ventilation, besides the fact that these systems are designed for this purpose and they do a good job of it is when installed properly, is the ability to recover heat from the outgoing airstream to temper the incoming air to improve comfort and lower conditioning costs. They come in two flavors. You've probably heard about HRVs and ERVs, and most people don't know the difference, frankly. ERV, a lot of people call them energy recovery ventilators. I call them enthalpy recovery ventilators, not only because that's more accurate, but because it indicates that it really is a different type of process, a different mechanism than an HRV, which is true. They both transfer heat between the exhaust and supply airstreams, but here are their differences. HRVs transfer sensible heat only, and heat, this is a physical principle, we can't change it. Heat is always transferred from the warmer to the cooler airstream, and the rate of heat transfer depends on the difference in temperature between those airstreams. Okay? Now, an ERV, enthalpy recovery ventilator, in addition to sensible heat, also transfers latent heat, which is basically moisture. And another physical principle, moisture always moves from the wetter to the drier airstream, and the rate of moisture transfer depends on something I call the delta M, which is the difference in moisture between those airstreams. Okay, so how do we make sense of that in terms of California homes? Let's take a simple example first. This is a conceptual diagram of an HRV. So this is it's summertime, outdoors, it's hot, not today, it's summertime here, but it's rainy and cool outside. But normally in the summertime, it's hot and dry outdoors in California, and indoors it's cool and air conditioned, okay? So the warm outdoor air is illustrated here by the red arrow. The supply air coming into the house is warm. The air being exhausted from the house is cool because the indoors is air conditioned, okay? So how do these things work? Well, heat always moves from the warmer to the cooler airstream, okay? So what does that mean? The heat from the incoming air is going to be transferred to the outgoing air. So under these circumstances, the HRV is effectively rejecting outdoor heat and retaining your air conditioning energy. Okay, and this is good. This is what we want. There's nothing wrong with this. There's no downside to this in California, and in the wintertime, it's just the opposite. An HRV will retain the warmth, the energy that you use to heat your indoor air. It will transfer that heat to the cold incoming airstream and effectively reject the cold. Okay, this is all good, right? Now, a lot of manufacturers and distributors and contractors will tell you that HRVs will significantly reduce your operating costs. The Home Ventilating Institute rates the recovery efficiency of these things, and they always report the maximum recover or the rated recovery efficiency. Now you need to know that the chances of your particular heat recovery ventilation system achieving those recovery rates depends on the actual delta T's that it experiences. And in California, we typically don't have the high indoor-outdoor delta T's that it takes to reach those high levels of recovery effectiveness. So don't overestimate how much it's going to reduce your operating cost. However, it's always true that HRV is going to improve comfort. Even if you don't see it in your electricity bill, it will take the edge off of hot air in the summertime and cold air in the wintertime that you're bringing in from outside. Now let's look at enthalpy recovery ventilation. And the misconception here is that an ERV will help control indoor moisture. The truth is that it's not a dehumidifier. We don't control the direction that it transfers moisture. ERVs they work great, and they're very appropriate and effective in hot, humid climates, hot, humid weather, where they reject outdoor moisture, and in really, really cold, dry weather where they help retain indoor moisture in the wintertime. However, when indoor air is wetter than outdoor air, which it often is in California climates and homes, an ERV will not help you get rid of indoor moisture. In fact, it will retain a certain amount of indoor moisture. So let's look at that. It's the same summer air conditioning condition, but indoors we haven't done a good job of controlling indoor moisture. So indoors is wetter, outdoors is drier and hotter. So an ERV is going to transfer moisture from the wetter airstream to the drier airstream. So it's going to transfer that moisture from the indoor airstream back indoors. Not all of it, but some percentage of it based on the delta M. Okay. So in general, these are the recommendations from HRV and ERV manufacturers. This is actually a point of controversy. We don't really have good data on the downside of ERVs in California. Some people say they can be used without any kind of harm. I don't know, but until we get that kind of data, I'm telling you that to be on the safe side, if possible, you want to use HRVs and not ERVs. People do install ERVs. Here's a sample installation at a new passive house in Point Reyes, California. The diagram that this is their diagram in the lower right, they call it an HRV. It's in fact an ERV, which is an indication of, there's some confusion between the two. But you can see from their diagram basically how it works. This is a great little house, and I took these photos during a GUTS tour, the affordable housing group up there which sponsored this project. Great bunch of people. They invited the public in to tour the place. There are several stages of construction. This was taken during the GUTS tour. And so I'm showing you here the ductwork, some of the ductwork that's involved in one of these systems. There are supply ducts, exhaust ducts, and exhaust grills and supply grills. And in this case, they look bigger than they are because these ducts are insulated. The actual duct that the air is moving through is much smaller than what we see here. Real quickly, supply ventilation basics. With supply ventilation, the source of air is controlled, and you can filter the air, as I've already said. It requires supply air ductwork to the rooms where people need it. Closed indoor areas do not disrupt the delivery of air to bedrooms at night. Positive pressure, it has an advantage, no downside in California. Now these things can be either energy efficient or extremely inefficient depending on the fan that you use, and that basically depends on whether or not the fan is integrated with the central air handler system or not. I advocate that a supply ventilation system be independent of the central forced air system, and this is getting to one of the questions we had earlier. Again, you're using a small, appropriately sized fan that you can operate continuously to maintain positive indoor pressure. This is the efficient way to do it. And if you come to my full day class, I'll have in my fan club, I'll show you all the different ways you can do this, including the filters available and the controls. Here's a picture of what I call it independent supply because it's independent of the forced air system. And here's a picture of one installed actually in a Greenpoint rated house where I was the Greenpoint rater. It's installed in the ceiling of the garage. The single duct is coming in from the outside. There's a filter in the box, and the fan basically sucks. Air goes through the filter first before it hits the fan, and then the airstream is split into, in this case, 3 different airstreams that go to 3 different bedrooms. Okay. Hit the wrong button. The other option is what I call forced air supply. There's different names for it, but basically all you have to do, builders, especially production builders, tend to want to do this because it's really cheap and easy to all they have to do is install like a 6-inch duct somewhere from the outside to the return side of the forced air plenum, and then whenever the forced air fan operates, it negatively pressurizes that duct and sucks in some amount of outdoor air. This is, in my opinion, this is, even though it's legal in California now, this is the worst case scenario for a lot of reasons, and I'll show you that on the next slide. Just to make sure you understand how this works, these forced air fans are not designed for continuous operation. They're designed to operate whenever the thermostat calls for heating and cooling. But ventilation, these requirements are every hour of the year. So if you want to do this, you have to put these fans are prohibitively expensive to operate continuously. So the code assumes that you will operate them 20 minutes out of every hour of the year, even when no heating or cooling is called for. That means that when the fan does run 20 minutes out of every hour, it has to emit 3 times your code minimum ventilation rate, which for the example of 60 CFM minimum times 3, it would have to emit 180 CFM of air when it operates, and that is very difficult, if not impossible, for these systems to do. So there are 3 compelling reasons not to do this. The first is that the forced air systems are just inherently 10 times oversized for ventilation. They're designed for a completely different purpose, and when you adapt them to continuous ventilation, you're basically creating more problems than you solve. The second reason is that occupants, all of a sudden, they notice that they have this. You hear this fan turning on and off every hour of the year, even when heating or cooling is not called for. Okay, so there's noise, and plus when the 20 minutes that it does blow, it's blowing the full amount of system air, and that air is untempered, so it's drafty, which is uncomfortable at best. And they also see the energy cost in their electric bill. If that's not enough to dissuade you from this option, the physics of the duct and the fan and the outdoor damper are such that it's very difficult to emit even the minimum code requirement outdoor air with these systems. There are workarounds. You can spend $1,000 extra to get a high-end air handler with an ECM, electronically commutated motor, but there are still remaining problems which I go into in more detail in my full-day class that I don't have time for here. So this is one of my last slides, and this is where I put this together to show this is just relative ventilation fan efficiency or efficacy. So the systems that I have talked about are on the left column, and they're arranged from the most efficient in terms of CFM of outdoor air per watt consumed to the lowest. So notice that exhaust, I'm using a default of 4 CFM per watt. For supply, I'm using 2. It's basically the same fan, but it has to be a little bit bigger. It uses more energy because of the filter and the additional ductwork. Balanced heat recovery systems are about half of that because they have 2 fans and even more ductwork in most cases. So they're on the order of 1 CFM per watt, more or less. But on the right-hand column, notice that the ratio of the worst, the best or most efficient fan to the least efficient is a factor of 50, which is huge. So in my opinion, I think we should not be using the one on the bottom, supply ventilation integrated with a standard forced air system which operates intermittently. The next most efficient or next least efficient one is balanced heat recovery, which even though, except for the bottom one, is least efficient, it's actually designed to do for this purpose. So this is another illustration of how you're not going to get everything on that shopping list that you want in a ventilation system. There are trade-offs, and this is just one parameter that you need to be aware of. So I'm suggesting that you don't use this least efficient system. People want to know, and the bottom line is, if you know, in summary, what are your options for meeting this requirement for continuous ventilation of new homes? If you just want to meet the code requirement at a minimal expense, use an Energy Star exhaust fan continuously. If you want filtered air, positive pressure, and reliable distribution, use a supply fan that's independent of the forced air system. If you want the best system money can buy, use heat recovery ventilation, but tighten the home as much as possible and make sure that it's functioning appropriately. Thank you.
Great. Okay. Well, we have a lot of questions, and so we'll get to them. Okay, so we've got a question. This was from early back, but I didn't want to interrupt you. So John Eckstein had said, So many times these continuous ventilation fans are located behind doors in bathrooms. Should we not also be encouraging the installation of transfer grills or jumper ducts if we are using a bathroom fan for whole house ventilation?
The answer is yes. I think transfer grills and other pressure relieving devices are even more important for central air conditioning systems, which have higher volume airflows, but it won't hurt. It'll help. But it won't completely solve the problem of indoor air distribution with exhaust ventilation systems.
Okay. And he also follows up, he said that HRVs will always improve comfort. His understanding is that HRVs typically run at a relatively low CFM rate. Is this sufficient to benefit thermal control, or thermal comfort?
Actually, HRVs or ERVs, let's talk about HRVs. Many of them, some of them have variable speeds, more than one speed, and their recovery efficiency is actually higher on low speed. Okay, so as long as you're delivering your design ventilation rate, low speed is actually an advantage when it comes to heat transfer.
Okay. And Brent wanted to know, with an independent supply fan system, how is the temperature controlled in colder months, or is it up to heating from another source?
Yeah, it's basically, there are a few ways that you can sort of passively try to temper incoming air with a supply ventilation system, but there's no active conditioning. You're basically relying on your heating system, and that's a reason that you want to deliver the supply air at or near the ceiling, so it has any hot or cold outdoor air has an opportunity to mix with indoor air before it reaches occupants.
Okay. And then Alan Marshall asked, how about conditioning forced ventilation system? And I guess you kind of did address that when you talked about the, not using it independent.
Yeah, I don't really understand the question.
Yeah, so Alan, type back in if you have a more clarifying question, because we don't quite understand that. John Eckstein asked, if you run an Energy Star exhaust fan continuously, then where do we want the makeup air to come from? Should we install a makeup air port to the exterior?
Good question. Good question. I'm going to anticipate the rest of the question. Our homes in California are nowhere near tight enough where we have to start poking holes in them to provide makeup air. Okay, we need to tighten our homes much further before you even have to start considering that. The makeup air, we have plenty of leaks in our homes. Unless you are, I'm going to give you a rule of thumb here. Unless you put a blower door in the house, and the blower door measures less than 250 CFM at 50 pascals, you don't need to poke holes in the house for an exhaust ventilation system. Okay?
Okay. I have some questions while we'll wait for some other people to type some in. I just want to confirm my understanding of the supply system, ventilation system. If you were to meet code, I'm guessing you'd still have exhaust systems in plumbed areas.
That's right. Okay, right. When we talk about these options for continuous mechanical ventilation, whether it's exhaust, supply, or balanced, those are that's a separate function, and they often are a separate system from the intermittent exhaust, which is required in rooms in bathrooms and kitchens. Right? Two separate functions can be accomplished by a single exhaust fan, but that's why we talked about the purpose of ventilation at the beginning of this presentation.
Okay. And then if you have an existing home, what do you suggest folks do first? Ventilate right or tighten? Or, I mean, my thought is that you wouldn't want to tighten until you have the ventilation.
Well, we don't have time to answer that question, but I encourage you to come to my class. I have done presentations for Build It Green existing home classes where we talk specifically about existing homes. The answer, like a lot of whole performance questions, is it depends.
Okay. All right. And John had a follow-up regarding that question you just answered before. He said, but the second part of the question is important. Is it not better to have makeup air rather than infiltrated air?
Well, yes, which was why it would be better to use a supply fan instead of an exhaust fan. You don't want to. There's no reason to start poking holes in your house, unless your home is extremely tight, as I just gave you an example of. Then you don't have any control over where the air comes in. Okay, so if you want to provide a purpose-provided makeup air inlet, okay, then you're wasting your time and your energy, and you're shooting yourself in the foot, because unless you've eliminated all the other holes in the house, then you have no reason to expect that your outdoor air is going to come in that hole instead of some other leak from your crawl space or your attic.
So Alan rewrites, can you run the air through something like an air handler that could run through a radiator?
I think you're getting I think that's too complicated. I don't see the point of that.
Okay. Richard asked, would you please repeat the minimum blower door reading where air supply on a continuous exhaust system is filtration?
Okay, I have a good slide on this in my full day class, but basically, you can measure the indoor pressure with a manometer while your exhaust fan is running, and unless your little exhaust fan is able to depressurize the house to at least 10 pascals, you don't need to install purpose-provided holes or passive inlets in your house. That's another way of putting it. For a 50 or 75 CFM exhaust fan, that's about 250 or 300 CFM 50 blower door reading.
Okay. We do have a follow-up question from Alan, or clarification. He's saying he lives in Truckee and the incoming air can be 0. I think that's why he was asking that question about the makeup air and infiltrated air and running through radiators.
Well, in that case, you know, if you're in a really cold climate zones 14 or 16 in California, I would suggest that you seriously consider a heat recovery ventilation system.
And I had a question. If you're using the supply system and you've got that positive pressure effect, does that affect comfort? Do you feel different?
No. It's any degree of pressurization or depressurization from these relatively small fans is nowhere near the 50 pascals that you generate when you're using a blower door. And if you've ever been in a house where a blower door test is being run, you don't feel that either.
Okay, you're right. Yeah. Okay. Well, we'll see if there's a few more questions. We've answered everything, but I have a couple announcements before we. Oh.
I have one from here in the room. Can an ERV be reverted to HRV by a homeowner as needed and easily, and should this be done? I don't know I'm not aware of, it would be up to the manufacturer. They would have to have a core, like a replaceable, like interchangeable cores, okay, like, and I think the answer is no, because the basic difference, one of the most basic differences between HRVs and ERVs is that HRVs require a condensate line. Some moisture will condense out, and that moisture has to be bled off through a line. It would be, so that's a consideration in converting. A few manufacturers do offer more than one core, but I don't know of any manufacturer that offers both an HRV and an ERV core. If somebody else is aware of that, please send me an email and let me know.
So while we're waiting to see if there's any more questions, just want to let folks know that we have a webinar coming up tomorrow, and it is on the Greenpoint Rated Climate Calculator with Tanaya Asan, Greenpoint Rated Program Manager. And so that's tomorrow, June 30th from 11 to noon. It is a free webinar for all. No CEUs will be offered. And then we have, if you have further questions after today's webinar, you're welcome to contact myself, or if it's technical in nature, please contact Judy, and there's her email there. But as Judy said, really to learn more, it's really worth taking one of those those free PG&E courses at either Stockton or San Jose in the fall, because then you'll get to see her fan club and get to ask all the questions that you have in every possible scenario. All right, we have another question that's come in. Mark is asking, would you think it's better on an exhaust-only approach to use a number of small fans versus one large, i.e. multiple bathrooms?
I would say that for cost reasons, to minimize your cost, it would make more sense to use a multi-port exhaust fan that's remotely located and ducted to several bathrooms instead of installing several individual fans. That would be cheaper and just as effective.
Okay, great. Well, we hope that you found this information helpful. We want to thank Judy again for coming here today.
My pleasure.
And thank you all for attending. If you do have additional questions, we'll stay on for just a few more minutes, but we will call the webinar officially closed. And again, we appreciate if you would take a few minutes to fill out the survey right afterwards, as it will help us improve our webinar offering. And we'll just wait a minute or two. Are there any other questions in the live room here? Yes, and as a reminder, this webinar is recorded and available at our members' webinar library, and also we'll have her PowerPoint slide available as a PDF, so you can listen to it with the audio or just refer to some of those slides, which are very helpful in understanding this.
Thank you.
Yeah, thank you guys. Oh, a question is coming in. Will we be sending us the survey? No, the survey, as soon as you log off, as soon as you exit the webinar, you should get an immediate survey right afterwards. Okay, we do have one more question. Or no, that's one we already answered. Stay on for a minute. Well, I always enjoy hearing this. I always feel like I learned something new.
Well, again, for those of you who didn't know much before, and maybe you're a little overwhelmed with how much there is to know about this, that feeling is normal. If you're feeling confused right now, that's normal. Most people have to hear these things, many times before it sinks in. And you're welcome. I'm all about helping people through this learning curve. So you're welcome to email me. Just be patient with the time it takes me to answer based on my workload. So thank you all for attending.
Yes. Okay. So there's no more questions that have come in. So we're going to officially stop the webinar, and we thank you all for attending.